we've handed back homework, and I have made some comments, so make sure that you take that into account. And now what we're going to do is we're going to complete the square for that ballistic arc that we were working on at the end of the previous session. So if you page back in your notes to that, we're going to do that, and then we're going to do some meter stick and pendulum measurements for classwork. And just to reinforce, homework 2 will be available tonight by supper time, hopefully. And then it'll be due Monday again at 8 a.m. And a different group will get their papers graded. Yeah. What? Ooh, that should be Tuesday. Sorry. I'll change that when I record it. Yeah, so sorry, Tuesday. Yeah, nobody has nobody has class Monday because it's Martin Luther King Day. Before we get to the complete the square business, I have a few things I want to do first. Just to remind you, this is the schedule for free tutoring over at SARC. Well, it's in the Engineering 1 building. Did anybody go yesterday? Nope. One person? Was it good? Is that a woman or a man? Okay. Was it good? He was friendly. He was nice. Okay, good. So now today there's some at 2 o'clock. Tomorrow, Friday, 10:30. So maybe Friday you'll be able to work on the homework. Hopefully I'll have that ready for you tonight by supper time or so. Now I want to do some clicking. We're going to do some iClicker, but we're going to do some short answers, alphanumeric. All right, so hit your refresh key, and what you'll come up with is the letter A as soon as I turn the question on. Now, the very first question is Cinci. Type in A or B. Okay, this is frequency BC. So type in a letter and then hit the send key. And then you'll get a check. All right. What is your name again? Yo, up front here with the brown shirt. What's your name again? Tristan what? Okay. Did you get a check? Did you vote? Okay. All right, 10 seconds to vote. 5, 4, 3, 2, 1, 0. Come on, you guys, vote. I simply want to know. Now, with this one, 94% of you say yes, and I'm going to mark both of these correct. So this is like a survey question. So if I do a question like this next week, when regular clicking cuts in, this is still practice today, but next week it'll be regular, regular pointage deriving from clicking. When I'm asking you a survey like this, where I just want to know your answer, I'll give everybody correct points on this. So this one, everybody, matter of fact, I'll just show you what it looks like. So I can mark both answers green. Okay, and nobody voted for anything else, which is good. So now, the next task that we're going to do is another alphanumeric data, but now we're going to form some sentences, and this is kind of a goofy exercise here. It's not a Chuck Norris question, but it's goofy. And it's about various snacking concepts. But what I want you to do is form a phrase like CBA from this code table. Sharks consume Cheetos. Now, you can't use CBA because I already invented that. All right, so you got to figure out some other snacking concept and then type in, and you got to hit the send key. All right, now the way that you get those letters It's just like numbers. You go up and down. So you should have your clicker should start on the letter A. All right. And then just go up to or down to B or M, or if you must, go to the letter N for your BFF, Justin Bieber. Yeah, and then you hit the right arrow key for the next letter. And then when you've got, so you've got 14 uh, characters possible. All right, we'll take a look at some of your answers. As a matter of fact, I can look at them right now. Oh my goodness. Oh my gracious. What? Oh yeah, I guess that's. Do more than just one letter. Give me a couple letters, at least. I mean, it's just kind of getting you used to. We're going to do a science question next, but this one's just kind of goofing around for practice. Yeah, don't just give me the letter A. Whoa. Josh, you got a problem?
Yeah, so like
Come on around over here.
I'm able to do it, but it keeps like dying on me. I think my battery's
Your battery is crap.
yeah.
Yeah, these things come with El Cheapo. Oh no, these are Rayovacs. You know what you gotta do is they're really loose. That's probably the problem here. Let's turn this back on. See, now it says full power.
Yeah.
So you got loose batteries in there. So maybe get a little tiny piece of tin foil and wedge it in there. Yeah. Okay, 30 seconds to get in your manifesto here. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 83 answers. Good. Now, what I'm going to do is let me make this a little bit bigger. Let's go over here. Okay, now this one I'm not going to grade correct because I asked for more than. Oh, look at this. AB period N. Okay. On this kind of a question, you don't want to type in a period. But, well, wait a minute. I know. Cheetos consume. Justin Bieber. I reluctantly grade this one correct. ABC, Cheetos consume sharks. Well, I guess. ABN, Cheetos consume. What? Justin ACD, Cheetos, sharks, French fries. Well, that must be a shopping list or some kind of invitation list or something. I don't know. B equals 0. Now, I'm going to make a point here. Now, this is a goofy question, but I'm not going to mark this one right. And it doesn't matter because you're on the scoreboard for today. You're going to get a bonus point if you're registered. So don't worry about that. But this one, I wanted a code sequence. I wanted a code string. And equal is not on the code table. Okay, B equals 0. Consume. See, that doesn't even make sense. Consume nothing. Oh, okay. Okay, CBD. Sharks consume French fries. Everybody knows that. CGI. Sharks always, I can't see, run. I think that's incorrect. Sharks can't run. They don't have legs. But I'll mark that correct. Whoa, CGO, JFD. Sharks always prefer walk whenever, whenever. That is mysterious. I believe that's a riddle. So, like when Gandalf and all those guys are trying to get into the mines of Moria and they don't know the password. That's what that is. Seagon, CGON. Shark. There's a lot of C's here. Sharks. Sharks always prefer Justin Bieber. I highly doubt that's correct. If you threw Justin Bieber in the ocean 1,000 times, 999 sharks would probably swim the other way. Sharks never run. That is actually correct. So I'll just give that. CJ, sharks walk, cheat. Yeah, okay. Anyway, so you can see. Whoa. There's some big ones up here. All right. I got to do this one. COD. Sharks prefer French fries. And whenever Justin Bieber mooches Cheetos. Ooh. That's what we call an advanced concept. Anyway, so now what I want you to learn from this. I mean, it's just kind of a goofy question for practice, but I'm going to ask you a scientific question next, same kind with the code table, a little bit bigger, and you're going to write in a scientific phrase or sentence. And on a test, on a midterm, I might give you a code question like this, and then I'll be able to give you partial credit by deciphering. Now, I won't do it this way. I'll use a spreadsheet to do it. Get all the raw data into a spreadsheet and then decode each symbol and put it together as a sentence. And then I'll read the sentence and then grade the sentence if it's correct. And so that's what's ahead. That's why we went through a few of the answers here. All right. Now, let's go to the next one. Let me get my cursor over here. Okay. So now we're going to have a scientific sentence. And do you remember this guy a few years ago? His last name is Baumgartner. And I can't remember his first name. He's a German guy. Can you imagine the rush of that very instant of time?
He doesn't hold the record anymore either.
What?
Yeah. It's a computer scientist, actually.
Yeah, right.
No, I'm not even kidding. He holds the record now.
You're not even kidding?
I'm not even kidding.
I never heard about it.
Yeah, you wouldn't. He's an unsuspecting looking guy too. He looks like a normal Joe.
A fake, a counterfeit. Well, let's do a scientific question. All right. So here's your question. Okay, now this is a righteous question. Describe the motion of free fall. All right, and use your sentencing skills, and you have a much bigger code table. So don't type in MCQ, maniacs are everywhere. That's just for an example. But if you read the code table, you can put together something that I think probably will be righteous. Okay, I can hear clicks. So hit your refresh key if you're blooped up, and then keep going. Brendan Botts, don't you have a clicker? Why not? What? Better get one. Tuesday is when we start doing clicks for real. Joshua, how's that holding up back there? All right. You guys, if you bought a clicker or rented one, it might be a worthwhile thing to go and buy some good quality batteries, because the batteries they normally come with when you buy them are really cheap, El Cheapo batteries, and they have a way of flaking out in the middle of a test, which you do not want. Okay, so just go get some energizers or some Duracells and be squared away. Okay, and I can see a few of you with answers. Let me take a look at what you got here. Yeah, you guys are doing all right. Whoa. 1 minute. So don't try to type in a sonnet or a poem or anything, but just 3 or 4, 4 or 5 is good. What's your name again? Mahmood, right? Yeah. Trying to learn everybody's names. Moody? Okay. Jennifer. Trying to remember these names. Derek. Derek, do you have a clicker? Good. Angel, do you have a clicker?
No, I gotta get it.
All right. Don't forget, Tuesday we start clicking for real. This is practice today and a bonus point. Okay, 30 seconds starting now. Ten, nine, eight, seven, six. Hit the send key. Don't forget that. 5, 4, 3, 2, 1, 0. Okay. Now let's look at this one, and this is a serious set of answers, and we're not going to be able to see all the things here. ACEH, speed is not constant. Okay, I'm going to mark that one correct. All right, it's green. Now, oops, this one. Now, the letter A is incorrect. Now, oh boy, look at this one. Let's grade this one. ACE, speed is not constant. DC and is accelerating until ground altitude. Okay, that's not bad. That's good. Yeah, it's not constant and it's accelerating toward until it hits the ground. Good. So, so you guys, this kind of a sentence here, it's not completely grammatical. I mean, the English department would rip it apart, but I got it. I got it, and you got it, right? And all of us got it. We know what that sentence is. I don't think there's a verb in that, the second part of that sentence. But now let's look at this fourth one here. ACH, speed is constant. That is wrong. Okay, 0 points for that set of 3 students. ACHS, speed is constant sometimes. Actually, that is incorrect as well. Let's just look at a couple more. Go down here. AQK, let's look at this one. Speed everywhere. Whoops. Speed everywhere. Whoops. Speed everywhere. Dude. AQK. Speed everywhere. Ground. No, that's not right. What is this? ASO? Is that what that is? So ASO is speed sometimes slower. That's good. That's not bad. ASO, yeah, I would mark that one correct. Now this is we're going to finish with this, but I want to point something out to you. This is a kind of a question that I might ask you legitimately on a test or a quiz. Well, probably on the midterm or the final. All right. And we'll occasionally do it in lecture in our class session as well. And the nice thing about this one is everybody can write in. I mean, if you look at the answers again, look at these answers. There's a lot of people that they're the only person that sent in that answer. Now ACH, there was 3, but all these other ones, just one person sent that answer, and some of them were correct. So the nice thing about this kind of a question is everybody can send in something different if the code table is big enough, and if you're creative enough, and still be right, still be correct. And that, my wonderful students, is lovely, because what that means is I'm drawing out the creativity and the brilliance that resides in you already. You've got it, and I'm trying to draw it out of you, and this is a good way to do that. The other thing, I'll just compare this to a multiple choice question. You know, if you think about it, well, and we'll have some multiple choice questions on midterm and final. Probably not on the quizzes, but on the final, yes. Multiple choice questions, I write the question and I write the answers. So you don't have any control over how to answer. You just have to choose one of them. One of them has to be correct, and the other 3 have to be incorrect. All right? And the trick is to write at least one incorrect that's tempting. Okay? To see if, to separate the sheep from the goats, if you really know your stuff versus if you're a little shaky. You might get tempted into the wrong answer. Kind of like the other day when I wrote down for a sign, I wrote down opposite over adjacent, and I wrote down tangent theta. Remember I did that, but I didn't catch you guys napping. Okay, but on a multiple choice question, I've got to have that, and those things are all cut dry. There's no creativity in there for you, but in this, yeah. And you're going to become scientists, many of you engineers, and many of you computer sciences, but it can be an art to finding a solution. It's to be creative and find a solution. Now, like that farmer's field, there was a little bit of creativity in that as to how you tackled it. But when you're getting into real life stuff where you're getting paid thousands of dollars a year by Lockheed or Siemens or Los Alamos or somebody like that, then you're going to have a great. It would be like having a great big code table, a gigantic code table, and you put it all together, and it might be the best way ever of solving the problem that you're posed with, whether it's some engineering or scientific quest. All right, so that's my little. It's just a workout. So everybody's going to get a bonus point today if you have a clicker and if it's registered, which is most of you now. Yeah, but then it's not free fall. The question was, is free fall, is the speed constant when it reaches terminal velocity? If that's the case, it's not in free fall anymore. It's not free. Okay, it's got errors. Terminal velocity is when the acceleration due to gravity is balanced by the air resistance that's pushing, back upwards. Kind of like when you stick your hand, you're driving down the turnpike at 70, and you put your hand out the window, you get a little bit of pushback. Okay, you're going this way, the air resistance pushes you back the other direction. So when you're falling down, the air resistance pushes you up, and when that bounces gravity, then you stop accelerating. So then it's not. So technically, you're never in free fall unless you're on the moon. Like the moon has no atmosphere, so no air resistance. And you could see the Apollo astronauts. They made a famous science experiment up there. They took a feather and a hammer, and they dropped them at the same time on the surface of the moon. They went right down. And you can't do that on Earth unless you're in an evacuated vacuum chamber. And they have a place up in Virginia at Langley Research, up in Virginia, the NASA Langley, where they actually have a gigantic chamber of that kind that they evacuate, and they can do that experiment. They do other stuff in there as well, test space capsules and stuff, spacecraft. But but yeah, so that's not free fall, and we're actually going to get into that here in a few minutes. So let's turn our attention to this business of completing the square, and I'm going to switch over the doc cam, but continue to record. Um, Quinn, I want you to sit here in these at the command post here, and when I ask you to change slides, just go with the right key there. Okay. So I'm on that first one now, and all right. Now I brought my notebook to school today, unlike the other days, so I'm going to use Graph Papyrus for doing this. Okay. And where we finished last time was, as you know, was right here, and we pretty much finished class asking uh, whether this set of equations down here corresponds to a parabola. All right, and the answer is, and we for simplicity we made our origin of coordinates to be the launch point for this object. But we assume that there is some horizontal velocity, Vx of 0, and we know that it stays that way the whole way through. All right. And we assume that there's some vertical velocity. In other words, it is going upward. It's contesting gravity, trying to go upward. All right. So those factors are in this equation, and we did a substitution here. We substituted x over Vx of 0 to get the parameter t, and then we substituted that in to the y equation and replaced all the t's with x's and with this constant underneath it, Vx of 0. All right, so we, and here's our diagram of, for instance, a baseball it's slammed upward. A baseball hit out towards the outfield, some kind of a pop fly or maybe a home run, and it's got some tilt angle, so it's got a little bit of x velocity and a little bit of y velocity, and eventually it's going to form a ballistic arc. And what we're going to prove is that it's actually a parabola. And so these two equations down here are basically what we've got. Now I'm going to do this a little bit differently today. And let me see if I'm going to use my blue ink instead of the pencil behavior because last time I also want to do something else here. Okay. So this is January 16, page 1. And we're probably going to go several pages here. Okay. So let's make a picture of our baseball. You know, I'm a visual learner, so I always start with a sketch of some kind. And so here's a snapshot at time t equals 0. And so, and here's the vector v of 0, the velocity. You know, so when it leaves the baseball bat, it's got that. And then here's components, lovely components. And did I say that we're going to be doing these at the wazoo? Yes. Okay, so here's the initial value of the y component of the velocity, vy of 0. And here's the initial value of the x component of the velocity. Now this thing's going to, I'll put a dot here to represent the origin. Draw another sketch. Okay, so this is the x-axis. And let me make this y-axis pretty good up here. Okay, so this thing's going to, let's see, it's basically 2 by 1, 2, 3.5. Okay, so this thing's basically, it starts out in this direction. Okay, so there's the direction of my initial vector, but it rapidly turns from that into a parabola that will look something like this. All right, and the ballistic arc, which we're about to prove, is a parabola. Okay, so here's the landing point. So let's see, we'll call this I for impact, and this is L for launch. And then up here, we'll call this point A for apogee, which is the fancy physics term for the part of the orbit furthest away from the center of the Earth. Apo meaning away, and GEE standing for the word geo or G meaning Earth. Okay, so this is impact. So this is where. So this might be the bleachers, or it might be right behind second base, or right behind third base, you know, or wherever it happens, or it might even be the pitcher's mound, you know, if it's a feeble pop-up. All right. Now our equations. Let's write our equation. Y is equal to, this is y of x, it's equal to Vy of 0 over Vx of 0 times x. Okay, that's the first term. And then the second term has g in it for the acceleration term. And that's 1/2 g. And then underneath there we had this Vx squared of 0. The square and then an x squared. And that basically comes in from the fact that we used Vx of 0 x divided by Vx of 0. So you can see this is t right here, x and this Vx of 0 in the first term. So Vy of 0 times t, initial speed times time. That's speed times time. This is what, you know, it's just constant velocity term, but we also have an acceleration term. Now the x squared in this Vx of 0 quantity squared, that's t squared according to this transformation over here. So that was our substitution. Now what we're going to do, a couple things that we're going to try to do here is complete the square. But before we do that, A student last time said, all right, let's factor out x. All right, so let's do that. So let's see, y equals x times the quantity Vy of 0 over Vx of 0 plus 1/2 g Vx squared of 0 times x. All right. So that is that is a parabola, but it's not the classical form of a parabola, y equals something times x squared. Okay. And actually we're gonna have a negative number in front of the x squared because it's an upside down parabola. Y equals a positive number times x squared would be a parabola that looks like that. Okay, so we don't have that. Okay. But we do have this upside down one. So eventually, and it's going to come from G. This factor here, don't forget, I'll write it up here. G is negative 9.8 meter per second squared for the acceleration due to gravity at the surface of the Earth. But we're just going to leave it as G for now. But remember, wherever a G form is found, there's a minus sign. Everything else here is positive. Okay, except for the G. So there's going to be a minus times something. All right. Now let's look at this thing here. Let's kind of analyze this. First of all, this is a ratio. It's dimensionless. All right. And as we said before, that is the tangent of theta, the launch angle. All right. Now we're going to keep that in the background till we need it. But yeah, this is tangent of theta right here, that term. I'll put parentheses around it up here. Okay. That's tangent of the launch angle. But I want to keep the V's in there because those are more dynamic than, those show us more about the initial conditions of stuff than just having the tangent of theta. But eventually we might want to care about that. Okay. So this one's dimensionless. Now, in this term, y is a distance. It's going to be measured in meters, and so is x. So this stuff here also, did I make a mistake there with something? That is not dimensionless. Let me make a look here. This is, we're going to have to go back to the originals here. Because look at this, we got an error here. Let me do this in pencil. G, the numerator here is meters per second squared. And the denominator is meters squared per second squared. V squared. So this is dimensions of inverse meters to the minus 1. So we've got a problem here. Let's go. No, but I need, oh yeah, that's right, because I have x, that's right. Okay, so this is right. Yeah, so this is meters, and then I've got meters out here in front. Okay, good. Yeah, that's right. So we're good. We're good. Anyways, so this is something that you can always check. Okay, and this is good to know. You know that this factor here, see this thing's going to come up again and again. This factor here with the G and the Vx squared of 0. All right, so it's good that we know that it's meters to the minus 1. And then this one is dimensionless. Okay, so the dimensions check out. Good. I had a little heart attack there, but we're good. All right. Now, question. Here's the classic math question. What are the roots of this equation, of this expression? In other words, where is y equal to 0? All right. Well, one place we know, you can just read it off here. When you see an x factored out and then a parentheses over here, no matter what's in the parentheses, if x equals 0, then y is equal to 0. And that corresponds to the initial position. That is how we set up our coordinate system up here. All right, so that's consistent. Now, the impact point is given by this. All right, so let's figure this out. All right, impact point y is also equal to 0, and so that means that Vy of 0 over Vx of 0 plus 1/2 g over Vx squared of 0 times x equals 0. Okay, so if you're looking at the roots, each factor could be 0. Okay, and for the first factor being 0, that's your initial position. Second factor being 0, this stuff here, I'll put it in parentheses. For that stuff to be 0, that corresponds to the impact point. All right. If it's a perfect arc, so in a real ballpark, if you land up in the bleachers for a home run, it's not going to return to y equals 0. It's going to be, y equals 10 meters or something like that. It's going to be a little bit above the field level, but for this example, let's continue with this. All right. So that means that Vy of 0, negative Vy of 0 over Vx of 0 equals 1/2 g times Vx squared of 0 times x. Okay, so now all we have to do is clear this fraction here over to the other side. And look, I've got in the denominator, I've got over here one factor of Vx of 0, over here 2 factors. So my numerator over here is going to cancel the denominator over here. And I've got a 2, and then the g goes into the bottom. So let's figure out if we can do this correctly. So minus Vy of 0, Vx of 0 over 2, no, minus 2 out in front divided by g. And that's equal to x. And now we can put a subscript here for x subscript impact. Okay. All right, so we've used, now we still haven't figured out formally, the normal function of a parabola, but this is doing pretty good. I mean, this is second degree. I mean, as soon as you see x to the second degree, ding, it's a parabolic arc of some kind. All right, now let's look at this a second. This one, this x coordinate here at impact, it's equal to minus 2 times a positive Vy of 0 times a positive Vx of 0 divided by a negative 9.8. So this is positive. Okay, so that's nice. And if we calculated it out, if I said, okay, this is 4 meters per second for Vx of 0 and like 10 meters per second for Vy of 0, then we can figure out the exact point. But, this is all I want to do for now. You could figure out the coordinates of that impact point in meters. But the main point is we've got it. We've got it from this equation. All right. Now let's try to complete the square. All right. We still haven't done that because completing the square is going to give us the coordinates of another point. All right, now I'm going to go to the next page for that. Okay, and I'm keeping this roughly in a square proportion so that I can put this on Instagram efficiently. Okay, so page 2. 1, 16, 20. Okay, so we're going to complete the square. So let me do a substitution now. This is going to be a little bit tricky. So I'm going to say that that quotient of the components is, I'm going to replace it with the symbol A. So the tangent of theta is going to be, you know, replace, and this just so I can write things a little more compactly. That's all. Right now, the G term is going to go into B. Let's see. Okay, I want this to be 1/2 G over Vx squared of 0. Okay, so this is going to save me a little bit of writing. That's it. Okay, so let's restate our equation of motion. So this is ax plus bx squared. Oh my goodness. That is nice. All right, now, one of the things that we'd like to get is y minus something equals a constant times x minus something else, quantity squared. This will give us, if we can get something like this, that'll give us the coordinates of the apogee. And we can get that over here by completing the square. Okay. Now the x has to be by itself, so I can't have a bx squared. So the first thing we're going to do here is factor out the b. Okay, so this is algebra time here. All right, so let's factor out a b, and we'll factor it out of both. Okay, so that's righteous. Okay, we haven't changed anything. We just kind of rearranged things. Now, x minus, I'll call it u, quantity squared, is equal to x squared minus 2ux plus u squared. All right, and actually, let me put it this way: x plus u squared, all right, is equal to x squared plus 2ux plus u. So now what we're looking at here is an x squared, and then this is going to be my 2u. A over b is going to be my 2u. And then I have to add in a u squared. And then I can compress everything down into this form. All right. So let's try to do this carefully. Okay, y equals b. All right, now. All right. I'm going to skip a space, and I'm going to re-express this stuff as 2 times 1/2 a over b times x. Okay, that's the same as this. But now I've got this identified as u. All right, and then I still have x squared over here, and a square bracket to close. So that means that I have to add in here the square of u. That's this term over here. Okay, u squared, and now I know what u is. I've got two u's right here. So I have to add in 1/4 a squared over b squared. Okay, and I don't need another plus sign. All right, so there's my completed square. But I can't do this without subtract. I got to subtract it off. I can't, this is an illegal procedure right here, unless I go minus b times the stuff I just added in, 1/4 a squared over b squared. All right. Now we got what we want. All right. This is a perfect square in the square brackets. This is some extra junk over here to the side. That's a constant, and it's gonna have a squared over b, and a 1/4 and a negative. And let's see, B has got my negative sign. So this is going to be a positive number when I get over here. And so let's get this thing dressed up in a way that is copacetic for our purposes. So 1/4. So I'm parking this junk over here with the y now. So plus 1/4 a squared over b. Okay. And remember, the dimensions of b are inverse meter. So b in the denominator has units of meters. So this is good. And a is dimensionless. Okay. Now the units of a are just numbers. All right. Now that's equal to, all right. Now I've got a b out in front. Nothing I can do about that. But on the inside, I have a perfect square. Now I'm going to dress it up. I'm going to put the x up front plus u, so 1/2 a over b quantity squared. All right, now we're going to, so there's my completed square. So my parabola, my vertex, right up here, the apogee, I've now got. All right. And what this tells you over here, this tells you how high it goes, because that's the y coordinate all the way up here at apogee. All right, so let's look at that. So y subscript a equals negative 1/4 a squared over b. All right, now let's put in a squared. Let's put the vx's and stuff back. So it's minus 1/4 vy0 squared over vx squared of 0 divided by b. Now, inverse b is 2 vx squared of 0 over g. All right, now we got a little cleaning up to do here. Let me get my red pen. By the way, you guys, I lost one of my red grading pens yesterday from all the red ink I had to write on your guys' homework. So this one, I don't know which one of these still works. Question? Because there's a B here and there's 2 down here. Okay, yeah, so those 2. Matter of fact, let me cancel this one. And I'll cancel the 2 down here. All right, good. So this is units of meters. Now here we got cancellation there. And we have a 2 up here and a minus 1/2. So let's see if we can make this a little bit more compact. Okay, minus 1/2 times vy squared of 0 over g. All right. Okay, so this is the maximum height. The maximum height above the launch point anyways. All right, so if you're playing up in Denver at the Mile High Stadium up there, or whatever they call it, Coors Field, add 5,280 feet to whatever this is. You know, that's your max altitude above sea level. But anyways, for this arc, that's the max height. All right, so what this let's look at this for a second. Let me write it again. And I'll write it this way: y max equals minus 1/2 v. Now what is this? This is y. square root of 0 over g. All right. Now, this, my wonderful students, involves potential energy, gravitational potential energy, which I'm going to give you a little blurb about today, and also the kinetic energy of the, because that's v squared. That has to do with v squared, and this has to do, potential energy has to do with the g. So this is basically here, students, this is a competition. Y max is a competition between the gravitational acceleration and however much kinetic energy you give it. You know, if you give it a lot of Vy, I mean, if you give it a lot of upward velocity, this is going to go way up there, all right? But if you have a really strong accelerator, you know, like if you're on the surface of, well, Saturn doesn't have a surface, but if you're on the surface of a really big planet, solid planet, and this was like 20 instead of 9.8 negative, then you would go up as high. Right? So this Y max, the factor of 1/2 comes in for the potential energy, and the G here, it's this. So this expresses a competition. All right. So this is a competition between you, or the source of that kinetic energy. So I'll call it the batter, and gravity. All right. Now the location of the vertex, that's going to involve the x component of the motion as well, because if you don't have any x velocity, then that's going to be straight up. You know, if you have a huge amount, you know, if you're like, now who's the biggest, who's the best hitter in baseball right now? Mike Trout. So if Mike Trout, you know, totally crushes a ball and it never goes over 50 feet above the earth, and it still makes a home run, that's basically a line drive into the stands. Then you've got a lot of Vx of 0, but you don't have a lot of Vy of 0, and you don't need it if you're Mike Trout. It's a total line drive into the stands, which can happen, you know. So let's look at x subscript a. So this is the y coordinate of the apogee. Let's look at x subscript a. All right. Now, x subscript a is this business in here, 1/2 a over b. So let's go 1/2. Now, a is my tangent ratio. So that's Vy of 0. Okay. Vx of 0. And it's not squared. And then inverse b is, let's see, 2Vx of 0 squared over g. Now here's my competition again. All right. But now, Adante, I've got some cancellation up here. I'm going to cancel one of these babies, one of the Vx of 0s, and this one down here. So now it looks a little different. All right. I still have a square of a speed, and I have, oh, and actually this is a minus here. This is a minus 1/2 up here. Okay. So it's, you know, whatever the sign is here inside the bracket, the opposite of that is your actual coordinate. So I've got a minus 1/2, and then Vy of 0, Vx of 0, and then g down below. Now this is complex. This is a complex competition. It's still, the batter's up here on the denominator. He does all of this. Okay. But now this is a mixed term. Okay. And this is kind of mysterious. Gravitation and Galileo's law of inertia, no such thing as horizontal gravity. We're still working on understanding all these in terms of general relativity and, making measurements and trying to understand all of it. And here's gravity down here. So the denominator, if you have a big denominator, you're on a solid planet with a lot of G for the surface gravity. Like the moon has a lot smaller. So if this were on the moon, with a lot smaller G, you're everything. You'd be a lot taller and a lot further down range, right? You can really launch stuff. Matter of fact, if you look at the movies of the Apollo astronauts, they can really jump. It's cool to watch them jumping. Question?
Yeah, you can actually factor out the 1/2.
What's that?
You can factor out the 1/2 on the second numerator.
No, I have it here. It's necessary. So, yeah. See, because this one is A over B, so this has to be 2 times 1/2 A over B. All right. Question in the back. Wait a minute now. Wait a minute now. Yo in the front here with the black shirt and the specs. What is your first name again? An. Okay, right. That's what I thought. And what's your name again? Daniel Goldman. Go ahead. Oh, I see what you're saying. Yeah. All right. Sorry. Ooh, good. Good eyes. Let me see. Do I have that in my notes? So this is 1/2 A over B. Oh, yeah, right. Okay, so this is, and I didn't go past this in my notes. So good, thank you. Okay, so this is just a 1. All right, so again, this is still a competition. Now I've got a minus sign out here in front. Now let's look at what we got here. For somebody launching in this, for this arc up here, you're going to have positive in the numerator, and then you have a minus sign down here in the denominator, and then you still have a minus sign out here in front. Okay, so you lose the factor 1/2. Right? So this is going to be positive. So just try to write that in, greater than 0, which it should be. It's going to be somewhere here, and it's going to be a little bit further, or it's going to be half as far as that's what I was thinking about. The other one, yeah. See, here's the other one. This is twice as far at x impact as the apogee x coordinate. So, in other words, it's a parabola. It's symmetric. In fact, let me just add one important. Oops, let me go the other direction here. Can you go to the next page, please? Okay, good, thank you. Okay, so it's important to put in a symmetry line here. All right, that's the halfway point of your arc. So if you hit it, so let's say that you hit it about a meter above the ground, okay? And the outfielder catches it over here about a meter above the ground. So you return to the same height. The parabola is symmetric about this center line. And that means that this distance here is half of the full distance. And this distance over here is half. It splits the parabola right in two. Okay. And so it's a good thing that you guys caught me here with this factor of 1/2 over here. Okay. We can't have to cancel that. But we still have a complex competition. This one's not just a competition of vertical kinetic energy. This one's got some horizontal. The more horizontal you got, the further down range your apogee is. Okay. And, the same effect for gravity. Strong gravity brings it a lot closer, makes this quotient smaller. All right. So all this stuff is related to, now I'm going to give you, go to the next page, please. I'm going to give you, I'm not supposed to do this, but I'm going to give you some instruction about energy. The gravitational potential energy, well, it's not that I'm not supposed to, but if I blindly obey the textbook, uh, has the form minus mgy. Okay, and so that's the GPE. All right. And so usually it's given a symbol, capital U, but sometimes you see other symbols. But we'll call that capital U of Y. All right. So U of Y is equal to minus mg y. And let's see, U of 0 is equal to 0, therefore. So you have no potential energy at your base elevation. And your maximum potential energy is at Y max. So U max is equal to U of Y max, which is the same as U of Y subscript A. All right. And let me go to the next page now. And let's talk about potential energy and calculus. This is page 3, 116, 20. Not yet. So U of Y is equal to minus mg of Y. Now, I forgot to specify, m is equal to the mass of the baseball, or whatever it is that you're launching into this ballistic arc. All right. And this is related to something called a force. Now, most of you have heard of potential energy, so therefore you must have heard of forces. And here's the relationship between forces and energy. Okay, there is a relationship between energy and force. So Sir Isaac Newton's concept of force, which we're going to study in a minute, is related to potential energy. And it's related to kinetic energy as well. Okay, now energy is the coin of the realm for most advanced physics, but engineers have to use forces a lot because they're actually building something. But like in terms of quantum field theory and black holes, we tend to use energy and momentum instead of force, because it's much easier to work stuff out. So here's the calculus relationship. Minus d by dy of the function u is equal to, well, let's figure out what it is. Minus d, what's d by d? What's the differential, the derivative with respect to y of this? Uh-huh. So that's equal to, all right, so the derivative would be minus mg. Now we've also got this minus sign out in front. All right. All right. And that is negative, less than 0. Therefore, it's downward. And that, my wonderful students, is the force due to gravity at the surface of the Earth. F equals mg. Now, another famous potential energy is for, in general, for a something that's not at the surface. If you're out in space, the potential energy is a function of r, your distance away from the Earth, and that's equal to minus g, capital G, Newton's constant, times the mass of the Earth, m subscript with a little circle with a plus sign in it, and times the mass of the baseball. So I'll put that m subscript b divided by r. All right. Now, what's the derivative with respect to r of basically 1 over r? I mean, we got a lot of constants up on top. So we got a 1 over r function. So what's my derivative? Right. It's going to be negative 1 over r squared. So that becomes g m Earth m baseball over r squared. And that's the famous inverse r squared force that Sir Isaac Newton, he was, if you read Sir Isaac Newton's book Principia, the mathematical principles of natural philosophy, which he wrote in Latin, and I read the English translation. He was working on this from like the page 1. He was setting everything up so that he could derive this force. And this is the force that rules the cosmos. Gravitational forces. So I don't even know what chapter we're skipping up to, like chapter 8 here. So this is like a preview of coming attractions. All right. But all this stuff, the reason I'm bringing that up is because if you look, here's the other thing that we need, kinetic energy. Go to the next page. Okay, kinetic energy, sometimes abbreviated T, is 1/2 mv squared. Mass times the square of the speed. Now, most of you have seen that before. The rest of you will get down to the nitty-gritty here in a week or two. But you can see here's the stuff that we had from Tuesday. You see it? See the 1/2 mv squared? You see the v squared in there? You see the mgh? Well, you don't see the mg and mv squared? Yeah. So and then here, so all this stuff, it's all working out just the way we want. All right. And so this is kinetic energy. This is, as I said, the vertical term or the vertical portion of the kinetic energy. The kinetic energy portion that derives from the vertical component of the motion. And then this up here, gravitational potential energy. That was Tuesday, and we just finished with it on a previous page. So all this stuff is in here, and this is the main rule. The force as a function of x is equal to minus d over dx of whatever the potential energy function is. And the utility is for this that a lot of times the potential energy and the kinetic energy are easy to work with. But eventually you have to figure out how strong to make something, how big a force to make, and so you just do the derivatives and stuff. And this is a scalar. This is a scalar function. And so it would be U of R for the gravitational potential. And then this would be, and this is actually the X component of the force. Okay, if you wanted the Y component, you would differentiate with respect to Y. If you want the Z component, you would different, if the potential energy, if you had a potential energy that was a function of X, Y, and Z, then you would do d by dx minus d by dy and then minus d by dz. Okay, so this is your general. I'll put a red rectangle around this baby. And so we're going to be using this thing this semester. So you're just looking at it. This is the mountaintop that we're heading to. All right. This is a little sandbox demonstration of why the simple baseball problem is loaded, as they say in that movie, The Diary of a Wimpy Kid, a loaded diaper. This thing is, I just saw it on TV last night. Just clicking through the channels. A loaded diaper. This thing's loaded. It's like your best lemon tree out in your backyard. Some of the lemon trees in my neighborhood, oh my goodness, they're loaded right now. And our mango tree is going to be doing good this year, I hope. But anyways, this is one of the mountaintops we're heading for. All right. Now, for the rest of the hour, I want we got about 50 minutes. And can you give me a meter stick? So we're done with instruction. You can hit the red button at the bottom. If you can, please. Or to switch to laptop. Sorry, switch to laptop. Okay, good. Okay, students. Shh, 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 shh. Friends, Romans, and countrymen. Uh, yeah, no, just one for each student. Yeah, you can do both. But hurry up. We want to collect this. Yeah, we want to collect it. Right, students, please be quiet now. Um, who is still working on their hand-in paper? Just one. Okay, hurry up, you guys. All right, hurry up. We want to go ahead and collect it from the people that are ready.
Something that would be helpful if you could put the letter of your table somewhere on the top. So A, B, C, D, E on the little flags on your table. Your H, just for ease of.
Also, put your group name at the top, your team name. Go ahead and start collecting. Whoever's got it. Quinn, you can start collecting over here. You guys almost ready over here? Yo, with the baseball, with the blue hat. Yo, with the blue hat. Get it. Yo, uh, with the blue hat. What is your name again? Sean. You guys ready yet? You ready? Hurry up. Quinn, let me see those. Who still has their turn in paper? Okay. Hurry up, you guys. You're closest to my table. Woohoo! Is that what your team name is? Here, let's see what these. Okay. Do we have your guys? Okay, one more. Okay. All right, great, thank you. This is pathetic. Okay, you guys got it? Kendra, can you operate this pendulum, please? Just be ready to do it in just a second. Just walk around. I'll get it from these guys. What's your team name? Did you? Nice. Okay, listen up. All right, I've got everybody's group work, and I'm just gonna go through some of the names. The group names, the Spectacular Three. It's right up here. Uh, B1. That's the name of the table set. Team 31 of Table A. Well, okay. You guys could change it if you. Here's a no-name group. The Justice League. Nice. Better group. Uh, Thalia, Alex, Kylie. I don't see a group name on here. Uh, the Ugly Ducklings table. Well, you know what the Ugly Ducklings became? A swan. AVX. Ooh, that sounds mean. Team name Asian Fusion. That's these guys over here, right? All right. Table F. You guys gonna have to work on that one. Team IDK. Oh, good one. I don't know. Okay. We're gonna change this to IKA. I know all by the end of the semester, hopefully. Team BTS, the back table student. All right. Team Dad. D. All right. From David, Andres, and Daniel, the DADs. Team name 954. I don't know what that stands for. I guess that's their IQ. Team 12. That's pretty good IQ. Team 12. Okay. F1. Team F1, also known as the Chimera Ants. Where are you guys? Diego, better. Whoo! You guys better crush everything, man. That's a good name, so you better live up to it. I3, Ray, Raj Kumar, and if you guys have a name. Team name Y equals Chris squared plus 1. Nice. TBD, actually our name. So that would be, to be determined. Okay. Uh, we not squared to calculate. E2. The Mad Lads. That's Trevor Kidd. Where are you at? Trevor Kidd? That's those guys back there. That's a good one. Team, that's what we. Okay. All right. I'll have to do some counseling with that one. Ooh, the Pythons with the Greek letter pi. Nice. Team name NCC for Nick, Carlos, and Caitlin. Very nice. Team Easy bake oven. Boy, I don't know if that's sweet or heinous, but it's good, you know. Ooh, the jumping Mandalorian nitros. Yes. You know, and see, here's the thing. Here's the thing. You've come up with a tough sounding team name, and then your grades stack out at the bottom. Then you got some splaining to do. All right, let's. Okay, Ann and Mike, you guys got to come up with a name. The Harvard Dropouts. Groupie naming. Okay, good. Now, I want on Tuesday we'll grade these over the weekend, hand them back Monday or Tuesday, and your homework is due Tuesday. It'll be up tonight. On Tuesday we're going to do the pendulum experiment, and one of the cool things about it, Kendra, let's switch over to the camera. No, that's the computer. All right, here's the camera, and go ahead and set it in motion, Kendra. La 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 la. Well, it's a little bit too violent. It's swinging that arm up there. That's better. La 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 la. Okay, stop it. Stop it. Now give it a very small displacement. La 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 la. See what the? Notice anything? Same time, even though the swing is wider or smaller in this case. Okay. So what we're going to be doing on Tuesday is calculating frequencies, and we're gonna keep one weight. You know, you can vary the weight, but we're going to keep one weight, and then we're going to vary the length of the pendulum. So right now it's at about 30 centimeters maybe. All right. And Thursday you're going to bring it all the way down to the floor if you want, or just above the floor, and time it out. And you're going to try to see a pattern in the frequencies, and you will. All right. It won't be easy to see, but you'll see it. Okay. Let's go back to the laptop. And just to repeat, your homework number 2, it'll be a PDF. Give me the PDF handout, not notebook paper, on Tuesday. All right. It'll be out about supper time tonight, hopefully, in web courses due Tuesday. Study up to chapter 4.3, and we've actually already talked about some of it. So go ahead and just crush all your way up to 4.3. You're dismissed.